So let's go ahead and get started. Today we will be focused on refactoring our MiniGPT code that we put together last week and refactoring it with a framework called JAX. JAX is a Python library for accelerated computation and programming, and it's designed for essentially high numeric computation and large-scale machine learning on GPUs and TPUs. Just around what we're going to do today, let's go up here. Let's look to the next slide. Last week we built this MiniGPT. Today we'll be making it sort of more performant, doing a quick rewrite in JAX, and our goal will be to increase performance of our inference of our MiniGPT with JAX. So hopefully at the end we'll have this sort of side-by-side comparison of doing inference with PyTorch compared to JAX with two models that will generate text from our Beatles lyrics, and then we'll sort of go from there. So let's write an agenda for today. So our agenda will be, firstly we'll do a JAX 101. So we get familiar with JAX. Then we will, sorry if I find my mouse. Then what we're going to do is we're going to write a basic JAX token generator. Basic. We'll do some training with JAX. We'll write our transformer model, and then finally we'll compare inference time. So those are the things that we're going to cover. So maybe we'll just start with a JAX 101 to get us started. So part of the reason why JAX is extremely performant, as you can sort of see on this graph, or hopefully you can see on this graph. You can see on this graph is that JAX uses accelerated linear algebra, which essentially is what XLA stands for. And JAX's performance comes from basically leveraging XLA's powerful capabilities to compile and optimize Python code for high performance computational tasks. And this combination sort of makes JAX a really potent tool for scientific computation and machine learning research and development. How I actually found and learned more about JAX was from some of the work that Hugging Face has done on their transformers. So if we go to Hugging Face transformers, I was looking at their repo for how they were building their transformer library, and it's super cool how they did it. But anyway, I was doing some research in here for something else, and I found JAX in here, and you can see there's a bunch of work that was done on some of the models specifically for JAX. I think it's Llama JAX is the one that I was looking at, or it might have been Mistral. Yeah, so you can see like some of the models have Flax, which works with JAX as an example. So you can see JAX is all in here. So part of it was just trying to learn more about how this works, but to break it down, trying to learn from some of the basics to start with. So let's write out some of the things that we're going to do here. So firstly, we are going to do some time comparison of random number generation. Then we'll apply matrix multiplication. We'll do a batched matrix. We'll use VMAP. I think that's probably enough just to get us started. All right. I don't know why this isn't formatted properly. Oh, I know why. Sorry. So let's set our agenda. We got these things to do. Shame I can't take these. Anyway, all right. So let's start with some random numbers. So I'm going to import the library itself here. Let's see if JAX is. So I'm going to import JAX.numpy as JNP. I'm going to import JAX from JAX, import grad JIT VMAP from JAX import random. All right, and then let's see, the key equals random dot key 0. Let's see, we got random. Random is not defined. All right, key is 0. So we got our random key here. Then I assume if I do something like this, x equals random dot normal, and then we do key, and then we want a shape of 10. What do we get? Do I need to define the D type? What if we print x? All right, so we got like this random, well, it's basically a random array of objects right now, right? So if I was to run this again, I get this random object. Let's see if this works. So size equals 3000, x equals random dot normal, and then we'll take the key. We'll take a size by size object. Notice there's a shape. We'll specify a D type as GNP float 32. This outputs this array. If we were to time how long it takes to do this, so let's use time it. And write JNP dot product of x by x dot t, and then we'll say block until ready. Say to run it on the GPU. So this is running. So 50 milliseconds is basically the average time it took for the code to execute, and 2.19 milliseconds represents the standard deviation of the execution times from the mean per loop. And this tells us that it was based on 7 runs with 1 loop each. All right, let's read through this. JAX NumPy functions work on regular NumPy arrays. Oh, that's cool. So I can also use NumPy directly too. So if I was to do import NumPy as NP, I can just mix and match them. So I could do x equals NP dot random normal. I'll do size equals size as type NP float 32. Let's cap this so the size is right. This is .as product. Now that we have this NumPy operation, let's just see if we get x from here. This is unmatched. Let's see, size of size. Oh, I got an extra. Alright, so I get this NumPy array, and then if I was to time this, I assume it's going to be slower than. So if I do a dot product of x dot t dot block until ready, we assume this is going to be less performant than the previous use case. Yeah, 37, so it's almost, it's at least double. It'll take double the amount of time because I assume the data is going to just transfer to the GPU every time. Okay, that's cool. So you can actually put it on device. Okay, so let's just do this. So the next thing we can do with JAX is I guess we can import device put, and then we can do x equals np random dot normal size equals. Let's just take the same code rather than write it out. All right, then we'll just do x equals device put x. Oops. Import from JAX import device put. Put x. So we should get something more performant than this because we're putting it on the GPU. Okay, so 18 milliseconds versus 37. So there's definitely value here, it seems, in using the some of the acceleration that they've added. So it seems like I can use JIT to speed things up. So if I was to run this, let's do this. So I remember JIT speed ups. And then let's create some of this code and run this. So what is this doing? It's running CellU. Then it took 1 millisecond. So CellU, as a reminder, is a scaled exponential linear unit. Alright, so let's use CellU here, and let's run CellU, which is scaled exponential linear unit for just 1 millisecond, and then I assume if we were to run this again, this means that we are getting this to run in 156 microseconds, and then it took 20 microseconds to run each loop. So it's super quick. It seems like it's pretty quick using JIT. So this is just some logic. Let's see how this works. And it seems like some adds. It has auto vectorization. That seems interesting. So let's maybe take a look at this. So this is matrix multiplication. So we just to go back here. We've done this. We've done this. We're just working on matrix multiplication right now, and just trying to learn a little bit about what JAX has to offer. So let's do this. And then we're going to apply, I guess, a batch in here. So define natively batched, apply. I'm just going to keep this super easy. Apply native batched native matrix with V, and I'm going to say return JNP stack, and then we're going to apply the matrix of V for V in V batched print and then we'll use time it native of batched X, then we'll say block until ready. Okay, and then I need to change this to, let's just call this VBatch. Then let's look at this. Let's get rid of this. Okay, so we've got 3.17 seconds. So this is basically returning a stack that runs against this operation of the list that we've defined in the VBatch. So maybe it's the best way to show this. If I show the batch text, let's print this. You can see I get this batch of objects that represent this shape, which is 10 by 100, and then we do a matrix multiplication of the two. So we're taking mat and do a matrix multiplication of this against the batch. 2.93 milliseconds, and apparently if I add JIT, it's going to speed it up. So let's copy some of this code. And let's alter it based on what we had. So we're going to call this VMap matrix, and then we're going to say apply the matrix with VBatch and see how. Let's see. Let's change this to VMap matrix. This should be faster. Let's find out. Okay, so then we get 104. The average is 114 microseconds versus 2.93. So there's definitely some performance increases in using VMap. What does it say about VMap? There's a vectorizing map. Creates functions with maps. There's a nice example. Cool. So it just creates a vectorizing map, I guess. That's cool. All right, so we learned a little bit about so we did matrix multiplication. It seems like, and we also did VMap, so we learned about JIT too in here. So we learned about VMap. We learned about JIT. We did not do grad, so let's maybe just see what grad is all about. Okay, so grad was the sum that we were talking about, so let's maybe insert this here. Okay, so we're just going to put grad in here. So let's do a sum. So what is this doing? It is doing, so this sum logistic is calculating the sum of the logistic function applied to the element applied to each entry in the input array of x, which we can see here. So let's maybe keep this, do an infinite, and we get a pretty close result, it seems like. Sorry, with finite differences. And then if we were to print the derivatives, apparently we can call grad on it. That's cool. Huh. That's pretty cool. Alright, we could probably spend a whole day with just doing JAX 101, but I think it might make more sense for us to jump from doing JAX 101 to actually writing some code. Pull up VS Code. Alright, so we got our JAX. What do we got going on here? Let's close this. So these are the things that we're going to do today. I'm going to call this JAX refactor.py. We are going to create a JAX token generator, a training, another one with another change with training with JAX, a transformer model, then we're going to compare the inference at the end. So let's go ahead and let's create a very simple JAX, some very simple JAX code. So I'm going to say import JAX, and then I'm going to say with open Beatles .text get R. Let's run this to make sure it works. Let's print this text. Okay, so we get our Beatles text, which is great. Then we're going to do create a character mapping, represent the vocab size. We'll do this string-based enumeration. Then we'll create our encode and our decode. And then let's just make sure it works. Let's copy this. just make sure that we can decode it. All right. So we know those are working, and then let's just create a very simple generate text randomly method. So we're just going to call this define generate random key, and then we'll do it of length. Do generated text of what we need to produce, and then we'll say random key, and then we'll get a sub key. Then we want to create the next token, and then we're going to randomly select the token. So we're going to say jax.random.rand int sub key. Then our shape will be empty. Min value, max value is the vocab size. Then we'll append it to the next token, and then we'll return the generated text. All right, and so here we need to pass these values in. So let's not do that yet. Let's do random key equals JAX, and then let's do a generated text. Then we're going to generate. Let's just generate 100. Then let's decode it. So let's do decode. So when this runs, it should just generate some random text for us. Unhashable type array. So we need to come back and fix our function. We need to actually get the item. Okay, so this produces some result. It's kind of garbage, but we're producing basically after this generate method is basically just generating more text and more text. All right, so next up we're going to sort of build on this in I guess a more serious way. So let's go ahead and let's mark this complete. And then let's next move on to sort of creating this training with JAX. So at the start here, I'm going to build on this and actually, what's the best way to do this? I'm going to use a data class, I think, to do this. I'm going to say import data classes, from data classes, import data class. And then I'm going to create basically a configuration here. So I'm going to say at data class config. I'm going to set my seed at 1337, number of iterations. We'll keep this small to start with. We'll set a batch size of 32, a block size of 8, a learning rate a 0.01, an embedding size of 32. We'll set our heads equal to 4, our head size equal to 64, and then we'll say number of layers is equal to 6, and then we'll do a dropout of 0.1. All right, and then we're going to save this as our config, and then we basically have this like a config that we can persistently use. So if I was to get config.seed as an example, I can get that from config. All right, so now we have our configuration set up, and you could probably think of these more as hyperparameters that we would set up. So we're going to basically build on this and add all the things that we added last time. So, but we're just going to write the code in a different way. So we're going to say class, I'm going to say feed forward mechanism, and then we're going to use nn module, and then we're going to say at nn.compact, and then we're going to define then we take nn, The reason why this doesn't work right now is that I think I need to import NN properly. So we're going to say import JAX.numpy as JNP. Then we're going to import flax.linen as NN. And maybe to give you a, let's go here and let's say JAX linen. So basically, this library Flax delivers an end-to-end experience who are using JAX. So it sounds like this is an example that we basically just copied right now. So you can add inline Flax modules in here, which should save us a significant amount of time. All right, let's jump back to our code. All right, so with this feed forward, we're then going to write our transformer block. So we're going to call this transformer block. I'm going to say nn.module, and we'll do something similar. We're going to call nn.compact, and then we're going to say define call self of x. Let's see what it gives us. Let's not do something that crazy yet. So we are just going to say call the feed forward method with x and pass x to it, and then we'll also add in a layer norm in here as well and return x. Okay. So now what we can do is we can actually create we'll create a class in here, and we're just going to call this JAX GPT. And then we'll put this here. So this will be basically the class for our model. So we're going to say number of layers. Is this int? And then we'll use compact. We're going to define. And then let's replace this boilerplate. So we're going to say x equals nn embed of the vocab size with feature size with x, and then we're going to say for in range of the number of layers, create a transformer block for each of the layers. Then we're going to pass, let's clean this up, prefer tabs versus spaces for what it's worth. X equals nn dense. Then we're going to return, we're going to return x in here. Okay. So we have generate. So now we're just going to expand on this. So we had random key before. We're just going to add in model params and length in here. And then we're going to say generated text, and we're going to say start with a space character to start with. Generated text. Generated text. Then we're going to go do this loop through the length again. Except we've got to now change this. So we're going to say x equals jnp.array with the generated text. And then we want to get the last item with the shape. To get the last token. Then we're going to get logits. Then we're going to get the random key, sub key. Did we do this earlier? Yeah, we did this earlier. Okay. And then we're going to get the next token, but we're going to change this slightly. We got a problem with this. Let's see. Oh, I think I know why. Yeah, there we go. Okay, so we're going to change the next token, and we're going to say jax.random.categorical. Then we're going to get from the subkey logits. We're going to say logits 0 minus 1. I'm going to say get the next token with logits from the last token. And that's essentially what this is doing. Okay. So now that we've got our next token, we are going to return it, but I'm going to make sure this is an int and not an item. So I'm going to say int next token, clean this up. And then actually I'm going to return, I want to just decode the generated text from this generator. Okay, so now that I have this set up, what I can do now is I can define the model. So I can take this out and I can say model equals GPT, JAX GPT. I can then specify the random key to initialize the model. So I'm going to say random key with the seed. I can do random key subkey. What's the subkey? To the split. I can specify the parameters by initializing the model with the subkey. We want to make sure that this is the size of 1 by 1 to start with. This is just the initial token that will be passed in. Then we'll say generated text equals generate random key with the model parameter. So we're just basically specifying the params that will go in the model that will go in this generate method here. So like before, what we're going to do now is we will prepare the data set. Oops. So we're currently started trying to do this. We're going to add training right now to this data set. So I'm going to say data equals jnp.array, and then we're going to encode the text. Then we'll do n equals ints, and then we're going to get 90% of the data. So we'll say times length of the data. We're going to call our training data, our test data. All right. Then what we're going to do is we're going to need to set up some training batches. Split into batches. Then we're going to call this define data batches, and then we'll say data batch size, block size. Here we'll create some indices. Let's say jax.random.permutation. Then we'll want this permutation to be the length of the data minus block size as our size. To essentially shuffle the data around. Okay, then we'll say indices equals indices length of the batches. Let me rewrite this. Indices, and then we're going to get the length of the indices divided by the batch size times the batch size. And this is to drop the last batch, basically, if it's smaller than the batch size. So if you look at all the batches, there might be a case where there's we might want to drop a batch if it doesn't necessarily equal the batch sizes that we have. For I in range 0, and then we'll do the length of the indices by batch size. Then we'll do batch indices. Let's get the next batch. So this is basically gets the next batch that we'll look at, and then it's going to yield. We should do yield data get that batch, and also get the batch size +1. So here we're basically just creating something so that we can hold our training data in some varied way that we can go use. So data batches will produce a randomized series of batches for us to do our training on. Okay, so with that, let's keep going and create a loss function like we did previously. So let's do loss function. I'm going to define the compute loss with logits and targets, and then we're going to use opdax, which I don't think is imported. So let's import opdax. And then while we're here, we're going to import from Flax training. We're going to import the training state. So Flax has these operators that we can use. They're super helpful. So we're going to say return opdax, and then we're going to get cross entropy with logits. Then we'll do JAX nn.1 hot with targets number of classes equal to the vocab size, and we're just getting the mean to compute the loss. Okay, then we can use that training, the sort of train state that I mentioned earlier. So we're going to create a class called train state, and then we'll call this key, and then what we'll do is we'll do define create train state with a random key in the configuration. Let's make sure that, so I'm going to say model equals, let's just make sure this is right, params equals model. We get the random key. We're going to get JNP ones with batch size by block size. Yes. Okay. And then we're going to say tx equals opdax, and then we're going to get the learning rate, and then we're going to return the training state and create it. Okay. Let's just say create training state. Okay, we learned about those JAX operators earlier, so we're going to call this JAX just in time. Then we're going to use our training state. We're going to do a step for training. So we'll do train step state x, y, and then add our dropout key. And then we'll say dropout key is equal to a fold in. We'll define a loss with logits. Then instead of this, we're going to change this yes to, and then we'll do one hots encoded labels with the vocab size with y. Maybe I can explain this. I'm going to apply the model to get the logits. Then we're going to use those to put this in our opdax soft max cross entropy. Then we'll have the logits to get the mean basically in each of our training steps. Let's get rid of this. Actually, this is loss. So then we can do loss grads, and then we'll do jax.value and the gradient, and then we'll pass our loss function and our parameters to that. We'll set our state to apply the gradients, and then we'll return state and loss in this step. Okay, then we'll also need an evaluator. So we're going to say define eval step. Let's see if this worked. Opdax. Does that look right? Number equals vocab size. Return labels, yes. And it returns the mean. Perfect. Okay. So then we'll do state, create, train step. We'll do the random key in our config. Does random key get specified? Yeah, perfect. Oh, well. And our configuration, and then we're just going to loop through this. I'm just going to start off with for I in range. What was the config called? Config.number of iterations. It's going to get the random key, subkey. We need to change this though. Let's back this up. Okay, so it's going to be state, and then we're actually going to get the next set of data batches with block size and the subkey. Yeah, that's right. Okay, then what we're going to do is going to get print, and then we're going to print the step with the evaluation loss in there. And now let's generate some text. So let's set the model. We'll some parameters. Say random key, and then I think it's just going to automatically generate the length. Let's check. Generated. Oh, I need to specify it. We don't want 1,000. We want 100. And then we're going to print the generated text. All right, let's give this a whirl. Use this random key. In all of that, we have actually now trained the model some way. There's a we've added in these states. I'm not too concerned about the loss right now. I'm just trying to replicate functionality to be able to do inference, but we kind of have our training set up in a way that we can start to move this. So we have training done. Our next thing that we're going to do is move on to basically building out our transformer model. So the next thing we're going to do is we're going to make some changes there. So we'll go make some of those changes. So the first thing we're going to do is we're going to use VMAP here. Where's our training? Let's find it. Get batch. Data batches. All right. So what we're going to do is we're going to use a VMAP. So we're going to call this dynamic slice VMAP, and then we're going to say JAX.VMAP, and then we're going to say JAX.lax.dynamic slice. Then we'll do in the axes of none, 0, none. I'm trying to think if there's an easier way for me to show you this. I am going to do this instead. Create code. Let's call this JAX helper.ipynb. Let's pull this up. Let's move this code there instead. Alright, so we got JAX, we imported, we created this map in our previous code. So we'll run this. Alright, let's keep going. We're going to get x equals JNP array, and then we'll keep doing this until 12. Okay. Then we're going to get some start indices. let's say JNP.array. I'm going to say get the first row and first column and get the second row first column. Then I'm going to say slice size. We're going to say is going to be equal to 2 by 3, so 2 rows, 3 columns. And then what we can do is we can perform this dynamic slice with these 3 values, and we should get a result. Okay. So we have this VMap that we have here. Now I'm going to need to modify the create function method that we have. So if I go to data batches, I'm going to say at jax.jit. And then I don't really love this name, so I'm going to change this name. I'm going to say define get batch, and then I'm going to say random key with our data. Then I'm going to say generate a small batch of random data of inputs x. Okay, so I'm going to say I equals random key. Let's just fix this. Random key with the shape equal to config batch size 1, a minimum value of 0, a maximum value, max value is equal to the length of the data minus the block size, so we get I, we'll call this IX actually. Then we can just use this dynamic slice map that we created earlier to slice the data. So I'm going to say data, and then I'm just going to say config.block size. And then we're going to say y is plus ix plus 1, and then we can return x and y here. And we're just basically using this slice, this VMap to make it easier for us to get a value from the batch that we've selected. Okay. We're also going to create a layer norm in here. So we're going to say class layer norm, and then we're going to say epsilon. Let's say point. We'll do a reduction axis. We'll set up NN compact and make a call at define call, and then we'll say mean2 equals jnp dot mean jax dot lax dot square of x, and then we'll do self dot reduction axes. And then we'll keep the dims, and then we'll do a mean, which will be just those. Then we'll take the variance, jnp.maxim of the 2. Then we need to compute the normalized inputs, and we can do that through xnorm, and then we'll return xnorm scale. This look right. Bias. We'll return the weights and biases. Yes. Okay. Now we'll specify our attention head again. Do we do attention? Nope. Okay. So we'll write a class for that. So we'll say attention. We'll write class attention and then module. The head size is int nn.compact. Let's give it some space. So we're just basically writing the part of the attention is all you need paper right now. So say self x, whether we're training on a we'll specify a key with the head size, no bias, a query, head size, no bias, value by the head size, no bias, trill, and then we have this fancy trill, and then we can do this over the shape. We can specify attention weights equals nn.softmax. Pardon me. JNP where trill. See if I figured it out. Transpose 021. Yes. Okay. Now we'll specify the attention weights for the dropout. So we'll drop some out. So we'll say nn.dropout config.dropout. With the attention weights, we'll say deterministic, not training. Then we'll return the attention weights with a dot product of value. Okay. Okay, now we'll specify multi-headed attention. So we'll say class multi-head attention. We'll say the number of heads is an integer. The head size is an integer. Let's see if it picked this up. So we're going to say concatenated heads with the attention self head, head size, x training, self number of heads. That looks good. The projected output with the output projection, then we're passing dropout again. Okay, that's multi-head. Feed forward should be pretty similar to what we had before, but let's just double check. Let's see. Let's just chain these together to make it easier. So we're going to say return, and then we're going to add dropout nn.dropout, and then we're going to say config.dropout. Then we're going to say nn.dense config dot embed size. I'm going to say nl relu and then dense, and then we'll do 4 times config embed size of x. Do we have configuration embed size? There we go. Let's just say deterministic, it's not training. I think I need another. NN dense, config embed size, NL relu with NN dense 4 times the configuration embed size over X. 4 times the configuration embed size over X. Yes. I think that's right. It's hard to sort of say. Okay, so feed forward is done. We need to add a block now that represents multi-head and feed forward. So we're going to do NN block, number of heads with their head size. And then we're going to say at nn.compact. We're going to make a call with X and training. This is multi-headed attention needs this, but layer norm also will need it because okay, that's where I need to make some changes. So layer norm. Okay, so I think I have my blocks set up. Then we need to go back to the model itself and really make some changes here. So now we're going to work on the model. So we're going to say number of layers is int. We're then going to say number of heads is int. And then we're going to say head size is also an int. We have our call in here. We now want to make some changes. We're going to say BT is X shape. X is equal to NN embed, and then we need to add some more in here. So I'm going to say plus NN embed number of embeddings of config.block size with the features embed size, and then I'm going to say JNP dot then we're going to do a loop. So we're going to say in the number of layers X is equal to block self number of heads where training. Do we have training in here? Yeah, I gotta specify X training bool. Then we'll do layer norm X equals NN dot layer norm of X, and then we'll return vocab size into this dense vocab, return X. Then we'll just we'll move basically the model. We're going to move this into the model. So we're going to say generate random keys, the length. We're going to set a default. I'm going to say 50. We're going to take out this starting. I'm going to say for in range length. Instead of having X in here, we're just going to say logits equals self dot apply params context, and then we're going to get this last item. Put params model context length. random key params context length. All right, so I have the okay, so I should have logits now. With the logits, I'm going to get a random key. This seems reasonable. Next token is essentially the same it was before. Let's just make sure that it's the axis is -1 and the shape is a 1 by 1. This shape is 1 by 1. Okay. Then I'm going to say next token, I'm going to say context equals context plus the next token of the axis of 1, and then we're just going to return the context rather than decode it. Okay. These look the same. So now we're going to go into training, but we need to make some modifications, I think, to do this. So we're going to say, what's the best way to do this? I'm basically going to remove all this code to go underneath the methods. Maybe not. I want to move this underneath because there's no real value, I don't think, in having it further up. So let's make sure the training is done right, actually. So we'll have a for loop in the training that will, let's see. Essentially do this. So we'll say do we not define it? Perfect. Okay. Remember that I changed this to get batches. Might need to change that, but let's see. Okay, so this is the state. Create the training state. Go over the number of directions. State loss is the training step by the get batch of, and then I need to change this line. So it's going to be, instead of next, it's going to be get the training step with get batch with the subkey train data with the subkey. Yes. Then rather than do on every step, we're going to say if the training step for every 100, let's print the loss. All right. And then let's just make sure that the train step is correct. Looks like it. The eval step looks right. So if I was to run this, train. All right. We have a really low threshold right now for the number, so it's only going to show once. Okay, so we're in a good place. So we're sort of in this step right now. We're on the transformer model. What I'm going to do now is I'm going to add in a step to basically save the model at the once it's finished through training. Ideally, you would do this based on fit, based on the validation loss and the training loss. But for the sake of this, I'm just trying to find out which is faster, so like I could optimize later. But so I'm just gonna try and save this. So we'll do param state dict equals serialization. And then I'm going to say with, so I'm going to say from flax import serialization. And then I'm going to say with, what shall I call this? With open outputs, GPT weights, dot pickle, and then I'm going to save this with pickle dot dump param state with the file. We may have used this earlier, so I'm just going to say weights. And then we don't have pickle imported, so I'm going to have to import pickle. And pickle is just a format I can use to store this state. So what I'm going to do is I'm basically going to train the model, save it in this pickle file, and then I'll be able to load it later. So once I've saved it, I can then you can consider this sort of like a so this should now go through and start training. So you can see here it's like doing some training. The training isn't that effective. There's probably some more things I can do with the model, but I tried to just write these super quickly. And then it'll save this pickle file. With that, so now that I've done this training loop, I actually can comment this out. And I can actually run the model itself against it. So say model equals JAX with the configs. I can specify the params by applying them. So I'm going to say subkey. I'm going to say actually random key with, we'll just specify ones to start with, but it'll be let's see. Let's specify the size. D-type, training is false. Then what we can do is apply the weights. So we're going to say with open, get our weights. And we'll specify the params. We'll say params state dict, and then we'll say params equals serialization from that. Then we'll say number of iterations, we'll say 100. We'll do a warm up of 3, and then we will warm the model up. So we'll say from in range warm up iterations. I think we already have this defined, but let's just make sure we do. We'll get our warm-up iterations. Just check one thing. And then we can do the warm-up. Parameters model apply. No. We'll just generate based on so it's going to be random key, the params, context, which would be yeah. Oh yeah. So that's our warm up. Now we can do actually, let's just see if this works. All right. So let's just take out the for loop completely. And we get this result for the output for printing the value. So we can now probably extend this out. So this is a little slow. So what we're going to do is we'll actually build on our generate method here, and we'll use partial JAX.JIT static args, and then we'll specify self and what is this? Self and length. Then we'll define our generate, and we'll call this generate_JIT with self, random key with the params and length. And then we will define a function called scan generate, where we'll take carry and x, and then we'll create a key and context equal to carry. We'll get our logits like we did earlier in the generate method. Set training is false because we're not training. We'll get a random key, and we'll do random jax.random.split of the key. We'll then set a new token, which is jax.random categorical, similar to what we have up here. In fact, I could probably just take it and copy and paste. All right, now we can specify the contexts, which will just combine these two together, but I'll just want the last item from context. Sorry, the first token. And then we can return random key, context, and the new token back from this scan generate method that we've set up. And then what we need to do is we can use we'll need to apply this. So we're going to say new token jax lax.scan. What does it say about jax lax? So it says we can specify a function in here. So we'll say scan generate with the random key. Context is not defined. With JNP.0, so we're just going to specify just a 1x1 shape for this, or 1 by block size. And then we'll take out XS equals none. Let me get this set up first. D type equals int np jnp.int 32. And then we'll take that out, and then we have our length, and then we need to close. Actually, yeah. Let's check we got everything. So we have our length, the tuple. I think we got what we need here, so then we just need to return. Let's clean this up actually to make it easier to see. Oops. Let's go back. So let's just try and make this. I keep clicking on the wrong thing. I'm trying to make this easier to read. So we have our jax lax scan here. Then we'll just return our new token. All right. So that we have that, we can let's do this. Just write a comment in here. So we're using jax.lax.scan, which is the product of, we have a function, the initialized values, xs and length. So here we have scan generate as our function. We're initializing this value of one by block size. We then have xs set as set empty, and then we set our length. All right, so now we can go ahead and we can use and write this generate method. So we can say model.generate_JIT with our subkey parameters and our length. And then we're going to get the and put this to a list, and then we'll decode the value. And if we run this, we get this output pretty quickly. We got a CUDA error here, so maybe what we can do is we can kill one of these. We still got this one, so let's kill this one. I can't remember if I need sudo. Or let me tell my password. All right, I think I killed the right thing. So if we run this again, I should get my Beatles lyrics back. And this is sort of a continuation of the Beatles lyrics. All right. So now that we have this, what we're going to do is we want to compare performance. So I'm going to edit this and we're going to warm up the tokens to token generation. So we'll do this by let's write number of iterations. Oh, sorry, number of warm up iterations. And we'll give it 10. We'll then say for I in the range of number of warm-up iterations, we'll get the keys. Let's change this. So we're going to go and import time it, because we need to time it basically to time these things. So we need to add in time it in here somewhere. So let's do this. We'll say define warm up. And then we'll specify the number of iterations. And then we can run this in time it. We'll get the total tokens. So we'll say our total tokens will be, that's what we're looking for, and then our total time will be equal to time it and the number, and then we can get our total time, and then we can print that out. So we can say print the average number of tokens generated per second to calculate the average, and then we'll print the average tokens per second. Then we'll print total time taken for warm-up. And then we'll print the average time per token. And that should give us what we need. So if we remove that and then run this, we get average tokens per second is 539. Now what we're going to do is we are going to expand on this and make it bigger. So we're going to do global random. Total length is going to be 0, and then we'll say with total length less than the desired number of tokens, it'll just keep generating until it reaches the total. So we got generated jet. We have our total length. And we'll just change this to the generation, what should we call this? Generation length, if I can spell. I also need to do the same up here, if we can spell length correctly. Less than the desired number of total tokens. Say plus or equal the length of the generate tokens. Then we'll print the total length. Oh, sorry, we'll print the decode the value. So this should get us our total. And then if we move this over, we can say the desired number of tokens is 1,000, the generation length is 100, and then we can go ahead and generate some tokens here, and our generation time will be time it. We'll say tokens per second is equal to the generation time divided by desired tokens, our average token per second, total time, and then maybe we'll do one more, print the average generation speed of tokens per second. So we give this a while, we get an output. Okay, so now let's move on to doing this for to compare the two together. So inference here we have from our GPT, and we'll replicate what we did with JAX over here with our GPT in PyTorch. So let's copy this method. We'll say while. Then we'll get the token, we'll decode the values. It's already warmed up, and then we have our generation length. And then if we run inference, we see we get this average tokens per second of 93. The total time was 10 seconds to complete. So if we copy these values, so let's just move out the print statements and run this again. See what we get. Still running. All right, so we get our average tokens per second is 99. So we'll just paste these values in here to see how this performs. We'll say PyTorch, speed, and then we'll move this over to the other value, and we'll run this for JAX refactor. So say JAX refactor .py. And then we get these results here. So we'll copy these up, and we can see that we get a, this might be easier to see. Well, let's put them side by side because that might be easier for us to look at. So you can see that the total time for generation with PyTorch compared to JIT is JIT is much more performant than PyTorch from what we can see here. If I just show them side by side, that might be easier to see. And obviously the GPU and other things will have an impact here, but you can see that if we look at the total time for generation, you got PyTorch that took 10 seconds, JIT took a significantly less amount of time. This isn't necessarily apples to apples. There's some performance improvements that we could probably make to improve this. If we look at why JIT is pretty nice. We have VMAP. We have this JAX.JIT and JAX lax scan and some other things that we're doing that I think just make JIT pretty performant from what we've learned today. And I think that's really interesting. Certainly learned a lot just playing around with this. But JIT is definitely a performant thing that we know we can look at in the future for any of these things that we do. So I still don't think it's an apples to apples comparison, but this gives a good overview of why folks are using JIT compared to PyTorch for highly optimized options.